The introduction. Good morning to everyone. I am Bajramshahe Shkodra, and today I'm happy to present to you our work on spray coated film organic memristor for neuromorphic application. This work actually is a collaboration between the Free University of Bolzano and the AFPFL in Lausanne under the project of the in-memory sensing. The aim of the project is to develop memristor-based devices for detection of process-specific antigen. My work today is the initial part of the project in realizing this kind of devices. Memristors are devices whose resistance keep memory of the path applied voltage, hence the name memristor. Actually, theoretically, these devices have been defined in the back 70s, but experimentally fabricated and tested only in 2008. This is the first memristor devices that have been experimentally tested. It is with a fairly simple architecture with a two platinum metallic electrode and titanium oxide as a switching layer. Afterwards, the research has switched has enhanced in developing biosensors based on memristor devices in this memristor-free standing structure. Also, lately, the concept of memtransistors has been introduced by using polymeric memristor switching layers. My work today focuses on the development and fabrication of polymeric memristor devices based on a sandwich structure. Here, at the memristor switching layer, we have chosen to work with a combination of two polymers, PSS and the PDA. Both of these polymers are solution processable polymers with very good conducting and mechanical properties. It's worth mentioning also that both of these polymers are biocompatible. The structure of our device composed of a glass substrate coated with the ITO, and then as a resistive switching structure, a blend between PSS and the PDA, while as a top electrode, we would have used gold. In the top of the slide, you can see a fabricated device, while in the bottom of the slide, there is the top view of the device ready to be characterized. Let me just move here. In the next slide, I will go through the details of the fabrication process. So first, we have prepared our PSS PDA blend. This was a composition between the aqueous solution of the PSS with the 0.3% of the PDA. In order to achieve a homogeneous blending of both the polymers, we have stirred the polymers at room temperature for 24 hours. Afterwards, in order to realize homogeneous organic film, we have spray deposited our solution. In order to achieve that goal, we have optimized several parameters of spray coater, like the nodule to the substrate distance, the hot plate temperature, which was set at 70 degrees Celsius, and the moving of the speeding arc, which was 150 millimeters per second. Right after spraying of the film, we have visualized the film by optical microscope. What you see here is that the drops are quite close to one another and relatively smooth, which is an indication of homogeneous deposition of the film. Afterwards, after a post-treatment of the film at 120 degrees Celsius for 2 hours, we have then conducted atomic force microscopy measurements. With the first picture, you can see the topography of the film. This allowed us to extract surface roughness of about 2.73 nanometers. Such a smooth surface actually indicates is indicative of a high quality spray deposition of our film. To finalize the fabrication of our devices, then we have proceed with the deposition of our top electrode. The top electrode was the gold, which was deposited through a shadow mask fabricated through a laser cutting. Since we have not used any adhesive metal layer between the PSS and the PDA blend and the metal electrode, the deposition rate of the gold was fairly low, 0.045 angstrom per second, but also very low Having complete the fabrication of our devices, then we have moved to the electrical characterization. The electrical characterization was performed at room temperature using a semiconductor parameter analyzer, having the always grounded ITO bottom electrode and using gold as a top electrode. We have conducted 10 repetitive current voltage characteristics, obtaining the desired loop hysteresis. To investigate the mechanism of resistive switching layer, and for the simplicity, here I have plotted only the last 10 scan of the previous graph. As you can see, actually, also down to the 10th scan, the device was able to maintain the Memristor behavior indicated by the hysteresis. Here, the arrows indicate the voltage sweeping direction. You can see that we obtain well-defined low resistive switching state and high resistive switching state. In fact, in the literature, the mechanism of such switching behavior of the device is attributed to the charge trapping model, coming from the hydroxyl groups of the PTA, which are presented in our lab. In this scheme, the charge straps are represented by these boxes. And as you can see, before applying any bias to the device is off stage. After application of the positive bias to our gold electrode, the traps actually start to get filled by the injection of the cations coming from the anode. Once the bias is reversed back, the charges get extracted back, and the device goes back to its old position. In order to confirm the findings in the literature, we then have replotted our ID characteristics in both logarithmic direction. In fact, the fitting of such plots are indicative of the switching behavior. As you can see, at the low voltages of about 2.6 volts, both the fittings of the high resistance switching state and low resistance switching state are at 1. This is indicative of the conducting switching behavior, omitted switching behavior, and most probably is due to the formation of the filament. While at high voltages higher than 2.6 volts, both the slopes of high resistive switching layers and low resistive switching state are higher than 2, which indicates the space charge trapping model, also attributed to the charge trapping model that I told you. So this result actually confirms the findings in the literature. Finally, we have also investigated the device stability over time by performing the validation test, maintaining the device at the bias of 1 volt for 10 to the 4th second. As you can see, we have well-defined low resistance state and high resistance state. For the current was maintained stable at the low resistance state for the entire duration of the test, while for the high resistance state, the device needed a stabilization time of around 2000 seconds, and then maintained the current stable at around 4 milliamperes. To conclude my presentation, we have presented the preparation and state position of the blend of Petrelli PSS and PVA polymers. Then we have used this polymer to fabricate resistive switching structure Memristor devices. And finally, we have characterized these devices in terms of morphology and electrical characterization. This approach is to present an easy and low expense approach for realization of Memristor-based devices in the future. I would like to thank our group, Sensing Technology Group in Bolzano, and just Cosmos Interface Laboratory in Lausanne. Thank you very much for your attention, and let me know if you have questions.